There's a very specific step inside advanced chip manufacturing where the margin for error is so thin it almost feels theoretical. You're dealing with layers measured in single-digit nanometers, patterns that don't just need to be precise, they need to be repeatable across thousands of wafers, day after day, with yields high enough to make the whole thing economically viable. Not just once in a lab, at scale, quietly. And for a long time, that repeatability was the real moat. Not the machines, because everyone knows about ASML's EUV systems. Not the materials, because supply chains, while restricted, aren't completely sealed. The real barrier sat somewhere more intangible: process integration. The accumulated, undocumented, experience-based knowledge of how to make all those steps work together without collapsing yield. That's where companies like TSMC built their edge. Decades of iteration, mistakes that never made it into papers, adjustments that only exist in internal playbooks, which is why something that's been happening over the last couple of years doesn't quite fit the old mental model. China has been moving up the process node ladder, slower than the leaders, yes, with constraints definitely, but not blindly, not randomly. And in at least one case, the way a specific node capability appeared suggests something uncomfortable. The gap between knowing the theory and running the process might not be as wide as we assumed. Let me be precise about what I mean, because this is where people either overreact or dismiss it too quickly. No, China hasn't replicated TSMC wholesale, not even close. Yield rates, efficiency, tooling ecosystem, still meaningfully behind. Anyone claiming parity is either misinformed or selling something. But there's a narrower claim that's harder to wave away. A process node, or at least a functional approximation of one, was assembled without the obvious pathway everyone expected: large-scale transfer of TSMC personnel. And that raises a question that's more strategic than technical. If you can reconstruct enough of a leading-edge process without importing the people who built it, what exactly was the bottleneck all along? Because the traditional explanation leaned heavily on talent. The idea was simple: without experienced engineers who've lived through multiple node transitions, you can't shortcut the learning curve. You need those scars. That assumption shaped policy. Export controls targeted equipment. Visa scrutiny tightened around semiconductor talent. The underlying belief was that know-how is embodied, that it travels with people. But what if that's only partially true? Let's step back for a second and look at how process knowledge actually exists in the real world. Some of it is explicit: published papers, patents, conference presentations, enough to map the broad architecture of a node, transistor design, interconnect strategies, lithography techniques. Then there's the semi-visible layer: supplier interactions, tool specifications, software configurations. Not public, but not completely opaque either. If you're deeply embedded in the ecosystem, you see fragments. And then there's the part everyone fixates on: tacit knowledge, the stuff that lives inside engineers' heads, the adjustments made at 2 a.m. when yields dip, the intuition built over years. The assumption has been that this last layer is the real barrier. I'm starting to think it's less of a wall and more of a compression problem, meaning if you have enough data, enough iterations, enough pressure, you can approximate that tacit layer faster than expected. Not perfectly, not cleanly, but sufficiently. Look at what SMIC managed with its so-called 7-nanometer class process. Again, not identical to TSMC's 7-nanometer. Different constraints, different tooling limitations, particularly around EUV. But still, functional. The interesting part isn't that they got there, it's how they got there, under constraints that were supposed to make that path impractical. No EUV access at the scale TSMC uses. Limited ability to import cutting-edge equipment after US export controls tightened in 2020 and expanded in 2022. And yet, through multi-patterning, process adjustments, and what looks like aggressive iteration, they produce chips that, while not cutting-edge globally, were far ahead of what many expected under those conditions. So where did the missing knowledge come from? That's where the story gets less comfortable and more diffuse. Because instead of a single channel, like engineers moving from TSMC to mainland fabs, what you see is a mesh of smaller transfers. Engineers trained in Taiwan earlier in their careers, but not necessarily at TSMC. Equipment vendors whose service teams understand process quirks across multiple clients. Academic collaborations. Reverse engineering of commercially available chips. Even the accumulation of failure data, which sounds trivial until you realize how valuable structured failure analysis can be. None of these, individually, explain a node. Together, they start to look like a distributed learning system. And that's the shift. The bottleneck isn't disappearing, but it's changing shape. Instead of needing a critical mass of elite insider knowledge in one place, you can begin to stitch together enough partial knowledge from multiple sources, and then let iteration close the remaining gaps. It's slower, it's messier, but under geopolitical pressure, slower and messier might still be fast enough. And that leads to a more uncomfortable question, not about China, but about the assumptions baked into US and allied semiconductor strategy. If the goal of export controls was to freeze capability by cutting off key inputs, what happens when the system adapts by reconfiguring how knowledge itself is built? I'm not saying the controls failed. That's too simplistic. They've clearly imposed costs, delays, inefficiencies. But they may also be forcing a different kind of innovation, one that doesn't rely on the same pathways the controls were designed to block. Which means the next part of this story isn't about whether China can catch up in a straight line. It's about whether the entire idea of linear catch-up was the wrong model to begin with. Because once you stop assuming that progress has to follow the same path as the leader, the map starts to look very different. There's a habit in this space, and I've caught myself doing it, where we treat process nodes like a ladder. 5 nanometer, 7 nanometer, 14 nanometer. You move down rung by rung, each step requiring the same sequence of breakthroughs the leader went through, just delayed. It's neat, it's intuitive, it's also misleading. Because when you look closely at what SMIC and parts of China's broader semiconductor ecosystem have been doing, it doesn't look like they're climbing the same ladder. It looks like they're building a parallel staircase out of different materials. Take multi-patterning, for example. Before EUV became viable at scale, even TSMC and Samsung relied heavily on it, essentially breaking a single layer into multiple exposure steps using older DUV lithography. It's slower, more complex, error-prone if not handled carefully, which is exactly why EUV was such a breakthrough. Fewer steps, cleaner patterns, higher yields. Now here's the part that matters. China didn't just fall back on multi-patterning because it had no choice. It leaned into it, pushed it further than most assumed was economically rational. From a Western perspective, that looked inefficient. Why stack complexity on top of an already fragile process? But under constraint, the calculation changes. If you can't access EUV at scale, your choice isn't between efficient and inefficient. It's between possible and impossible. And suddenly, squeezing more out of DUV isn't a fallback strategy. It becomes the main line of effort. What that requires, though, is brutal iteration. You're effectively increasing the number of steps in the process flow, which multiplies the points where things can go wrong. Overlay errors, line edge roughness, defect density creeping up in ways that compound across layers. In a system optimized for efficiency, you avoid that. In a system optimized for resilience under restriction, you tolerate it, as long as you can keep yields above a survivable threshold. That's a different mindset, and it shows up in how fabs prioritize outcomes. TSMC optimizes for yield, cost, and performance at global scale. It has to. Its entire business model depends on it. SMIC, operating under constraints, can accept lower yields for specific strategic outputs. If the end goal is enabling a domestic ecosystem, say producing chips for Huawei's Kirin line, then the definition of success shifts. You don't need world-beating margins. You need working silicon. That distinction sounds small, but it changes everything about how process knowledge is applied. Because once the pressure is on make it work rather than make it optimal, the space of possible solutions expands. And this is where the distributed knowledge idea becomes more concrete. Imagine you don't have a perfect internal playbook for a given node. Instead, you have fragments. A supplier who understands how a particular etching tool behaves at certain tolerances. A research group that has modeled defect propagation under multi-patterning. Engineers who've seen similar issues at older nodes and can extrapolate. Teardown analysis of existing chips revealing layout and density trade-offs. None of these give you the answer, but they reduce the search space. So instead of wandering blindly, you're iterating within a constrained map, one that gets refined every time something fails. And failure, in this context, isn't just a setback, it's data. That sounds obvious, but in semiconductor manufacturing, structured failure data is incredibly expensive to generate. Each wafer run, each process tweak, costs time, materials, and machine availability. Which brings me to something that doesn't get enough attention: scale of experimentation. China's domestic demand for semiconductors is enormous. Even under sanctions, even with limited access to the most advanced nodes, the internal market provides a kind of buffer. You can run imperfect processes and still have a place to deploy the output. Not always in flagship smartphones, but across a wide range of applications: industrial systems, automotive, consumer electronics that don't need bleeding-edge performance. That creates a feedback loop. More production, more data, faster iteration, incremental improvements in yield. It's not elegant, but it compounds. Compare that to a company operating at the absolute frontier. At 3 nanometers or below, the tolerance for failure is razor thin. Customers expect near-perfect yields because the economics demand it. There's less room to learn by doing at scale because the cost of mistakes is so high. Different environments, different optimization strategies. Now, layer on top of that the role of equipment vendors. Even with export controls, not every interaction disappears. Maintenance, legacy systems, indirect knowledge flows, these don't just switch off overnight. Engineers who service tools across different fabs accumulate a kind of cross-context understanding. They may not transfer proprietary recipes, but they understand behaviors, limits, failure modes, and over time, those insights diffuse. Slowly, imperfectly, but enough to matter. This is why the no TSMC employees framing is technically correct, but strategically incomplete. Because the knowledge ecosystem around semiconductor manufacturing is broader than any single company. TSMC sits at the center of it, yes, but the periphery, suppliers, academia, adjacent industries, carries echoes of that knowledge. And under pressure, those echoes can be amplified. Let me push this a bit further, because this is where the strategic shock comes in. If process knowledge can be approximated through distributed learning, then the effectiveness of export controls becomes time-dependent. In the short term, they bite hard. They create immediate capability gaps, delay projects, force redesigns. But over the medium term, they may incentivize exactly the kind of system that reduces reliance on single points of failure. More domestic tooling efforts, more focus on older, more controllable technologies pushed to their limits, more tolerance for inefficiency in exchange for autonomy. I'm not saying this leads to parity, but it does lead to something else: divergence. Instead of one global technology stack led by a few companies, you start to see parallel stacks emerging. Not identical, not fully compatible, but each sufficient for its own ecosystem. And once that happens, the question shifts again. It's no longer just, can China reach 3 nanometer? It becomes, does it need to in the same way everyone else does? Because if your system is designed differently, if your constraints force different trade-offs, then the endpoint might not be a mirror image of TSMC at all. It might be something that looks less efficient on paper, but is harder to disrupt. That's the part I think a lot of analysis is still underestimating. Not the speed of catch-up, the shape of it. There's a counter-argument here that deserves to be taken seriously, because on the surface, it looks convincing. Even if China can approximate a 7 nanometer class process using DUV and aggressive multi-patterning, the argument goes, the real game has already moved on. TSMC is deep into 3 nanometer, working toward 2 nanometer with gate-all-around architectures. Intel is trying to re-enter the race with ribbon FET. Samsung is pushing its own variants. The frontier isn't standing still. So what exactly is China catching up to? A snapshot that's already outdated. And if you frame it that way, the gap doesn't just persist, it widens. There's truth in that. You can see it in the power efficiency of chips, in transistor density, in the kind of workloads cutting-edge nodes can handle. AI training, high-performance computing, advanced mobile processors, these are not trivial differences. they translate into real-world advantages. But there's a quiet assumption embedded in that argument that I'm not fully convinced holds. It assumes the frontier defines the entire game, that everything below it is just a lagging indicator, waiting to be replaced. Look at where most semiconductors actually live. Not in flagship smartphones, not in hyperscale data centers. They're in cars, industrial machinery, household appliances, telecom infrastructure, defense systems. Nodes like 28 nanometers, 45 nanometers, even older, still massively relevant because they're reliable, cost-effective, and good enough for a wide range of applications. Now add a layer of geopolitics. If you're China and you're facing the risk of supply disruption at the high end, your priority isn't just to win at 3 nanometers, it's to secure the entire stack, from legacy nodes up to whatever level you can sustain domestically. That changes the optimization problem again, because instead of pouring all resources into chasing the absolute frontier, you spread effort across multiple layers. Stabilize and scale mature nodes to reduce import dependence. Push mid-range nodes like 14 nanometer and 7 nanometer class into viable production under constraints. Invest long-term in next-generation architectures, even if they lag. It's less glamorous, but it's strategically coherent. And here's where I want to challenge my own earlier framing. I said the bottleneck might be a compression problem, that enough data and iteration can approximate tacit knowledge. That's directionally true, but it risks underplaying something important: time. Even with distributed learning, iteration cycles take time. Equipment limitations slow feedback loops. Lower yields mean more wafers needed to reach the same level of insight. There are physical limits to how fast you can run experiments. So the gap at the frontier doesn't just exist, it compounds. While China is extracting more from DUV, TSMC is refining EUV processes, improving yields, integrating new materials, moving toward backside power delivery. Each generation builds on a cleaner, more efficient base. That's hard to replicate indirectly. And this is where the system starts to split into two different tempos. One moving fast at the edge, driven by a tight integration of design, manufacturing, and tooling. The other moving steadily under constraint, optimizing for resilience and sufficiency rather than absolute performance. Neither is static, but they're not synchronized. Now bring AI into the picture, because this is where things get less linear. Advanced AI models do benefit from cutting-edge nodes. Training large models efficiently often requires the best hardware available, which is why access to GPUs fabricated at leading nodes has become a geopolitical issue in itself. But inference, actually running those models, can be distributed across less advanced hardware, especially as models get optimized. If China can't fully match the frontier in training efficiency, it can still build massive inference capacity across a wide base of good enough chips. Different architecture, different bottlenecks. And again, the pattern repeats, not matching the leader step for step, but reconfiguring the system around constraints. I'm not entirely certain how far that approach scales. There are limits. Energy consumption, latency, coordination costs, they all start to matter at scale. But it's not trivial either, which brings me back to the original discomfort. We've been framing this as a race with a clear finish line. Who gets to 2 nanometers first? Who dominates EUV? Who controls the most advanced fabs? All of that matters. A lot. But underneath it, there's a second layer of competition that's less visible. Who can build a system that continues to function and improve when key inputs are restricted? That's not about being first, it's about being hard to stop. And if you look at it through that lens, some of the signals coming out of China's semiconductor ecosystem start to look different. Not impressive in the usual headline sense, but persistent, which, in a long game, might matter more than a single node advantage. I'm not saying this overturns the current balance of power. It doesn't, but it complicates the trajectory. Because instead of a clean gap that either closes or stays open, you get overlapping capabilities, different strengths, and a system that's adapting in ways the original constraints didn't fully anticipate. And once a system starts adapting like that, predicting where it lands becomes less straightforward than most narratives would have you believe. There's a moment in this story that keeps bothering me, and it's not a headline moment. It's quieter than that. It's the point where a system stops trying to replicate the leader and starts optimizing for its own survival conditions. Because once that shift happens, you can't evaluate it using the same scorecard anymore. If your metric is, are they as good as TSMC at 3 nanometer? The answer today is clearly no. Probably still no for a while. The gap at the frontier is real, and it's reinforced by tooling, ecosystem depth, and decades of accumulated refinement that you can't shortcut cleanly. But that question is starting to feel slightly misaligned with what's actually unfolding. A more useful question might be, can they sustain a semiconductor ecosystem that meets most of their strategic needs without external dependence? That's a lower bar technically. It's a higher bar systemically, because it requires coordination across everything: design, software, materials, equipment, packaging, talent pipelines, financing. Not perfection in any single layer, but enough functionality across all of them that the system doesn't break under pressure. And this is where I think the almost in that title matters more than it seems. China didn't replicate a TSMC node cleanly. It approximated it, bent around constraints, accepted inefficiencies, filled gaps with workarounds that, in another context, might be considered suboptimal. Almost doesn't sound impressive, until you realize that in complex systems, almost is often enough to unlock the next stage. A chip that's slightly less efficient still runs software. A process with lower yields still produces volume if you can afford the input cost. A domestic tool that's less precise still contributes if it reduces a critical dependency. These aren't elegant victories, they're cumulative ones, and they add up. Here's my read, and I'm putting a bit of weight on this so it's not a throwaway line. We're moving from a world where semiconductor dominance was defined by a narrow set of companies at the cutting edge, to a world where there are at least two partially independent ecosystems, each good enough in different ways. Not equal, not interchangeable, but resilient within their own boundaries. That has consequences that go beyond chips. Supply chains start to fork, standards drift, software ecosystems adapt to different hardware assumptions. Even geopolitical alliances begin to reflect technological compatibility, or lack of it. It's a slow fracture, not a clean break. And once it progresses far enough, reversing it becomes extremely difficult, even if the political incentives change later. Let me check myself here because there's a temptation to overstate this. There are still choke points. ASML's EUV remains one, certain advanced materials, high-end EDA tools. These are not easily substituted, and they still give the US and its allies real leverage. So no, this isn't a story of control evaporating overnight. It's a story of control becoming less absolute over time, gradually, unevenly, sometimes in ways that aren't obvious until you look back. If I had to put a prediction on the table, and I'm aware predictions in this space age badly, it would be this: China does not need to fully replicate TSMC at the frontier to materially change the balance of technological power. If it can consistently produce good enough nodes domestically, while continuing to close parts of the gap through iteration and selective breakthroughs, the strategic outcome starts to shift anyway. Not dramatically in a single year, but noticeably over a decade. And here's the part I'm still wrestling with, the open question that I don't think has a clean answer yet. Have export controls, in trying to preserve a lead, accelerated the creation of a parallel system that eventually reduces the effectiveness of those same controls? I don't mean in a simplistic cause and effect way. I mean structurally. By forcing a different kind of innovation, by rewarding resilience over efficiency, by pushing an entire ecosystem to learn how to operate without its previous dependencies. If that's true, even partially, then we're not just watching a race. We're watching the rules of the race change while it's still being run. And the uncomfortable part is this: the winner might not be the one who gets to the smallest number on a process node chart. It might be the one who builds a system that keeps moving, even when parts of it are cut off.